In this video, I'm going to talk about the limits at infinity and how does a function with a variable such as x would behave as x approaches to positive or negative infinity. So if you haven't just learned about the limits at infinity points or the introduction to limits, you can click the link above and check the video that's going to cover that topic. But for this one, the three main topics that we're going to cover, it's going to be the limits at infinity for constant and polynomial functions. Also, it's going to be for rational functions, and at the end, it's going to be their behavior as the infinity point is going to reach and go for the exponential and logarithmic functions. So for the constant function parts, if we want to just define a definition, we're going to say that in mathematics, a constant function is a function whose output value is same for every input value. So if we just want to get this one just evaluated graphically, it's going to be something like this. And by the way, from both points, this is going to be continuous. I just didn't want to get it out of the shape. Anyway, so for any input that is going to be applied in the function, we're going to get 3. So does not matter how large or how small the number is going to be, even at the highest point, which is going to be positive infinite, we're going to get still 3. And as we just learned, it's going to be the same for this one, which is going to be the limit of -1 as x approaches to negative infinite. But notice that x is reaching for this one to positive infinite and for that one to negative infinite. But we earlier discussed that it's going to be the same output for any input. So actually does not matter if the x approaches to negative or positive, and either for this one. Now for the polynomial functions, we're going to first check the formats, and we'll see it's going to be something like this. But let's check that the first and second one that are also short are going to be a polynomial function or not. As we could see, the x squared is going to have a format like a times x to the power of nth. That we could say a is 1 and n is a number like 2. And same goes for the second one, which could say that the a could be 2. I'm sorry, it's still 1. And the n, this time, it's going to be 3. So what we do know is that we're dealing with polynomial functions. And for this one, let's say that the limit of x squared when x approaches to positive infinite, we do know that positive infinite is a huge number. So if it's going to be squared, it's going to be also a huge number. So we're going to write down positive infinite. And for the second one, it's going to be the same as we noticed. Infinite cubed, well, infinite is not an exact number, we do know that, but mathematically we do know that it's a huge number, that is way too big, or in positives or in negatives, that it could be not necessarily undefined, but we cannot actually write it down. So when it's going to be cubed, it's going to be still positive infinite. So let's say that it's going to be the same limit, but this time the x cubed is going to reach to negative infinite. For this one, still it's going to be a big number, it's going to be infinite, but as we notice, it's going to be a negative number because a specific number cubed, when it's negative, it's going to be multiplied 3 times or multiplied by an odd number, which is going to make the number negative. Right. So for the third one, it's going to be a bit complex, but it's more like a polynomial format. It's longer. The format is more like it. So let's say that we're going to directly substitute the negative infinite to the function. We might get into a confusion that this function could be a bit confusing because we cannot guess whether if it's positive or negative infinite. But as we see, we can find the higher degree, which is negative 3 x to the power of 8th, and write it down by itself. So the reason that we're doing this is that the other two terms are lower and also insignificant compared to this. So the limit of negative 3 x to the power of 8th as x approaches to negative infinite. We do know that negative infinite to the power of even number, it's going to be infinite, but when it's multiplied by a negative number, it's going to be negative. So this is going to be negative. And also we're going to do the same for this one. The 4x squared minus x to the power of 5th plus 2x to the power of 4th. We're going to select the highest term and we're going to write it down, which is the more significant one. Well, technically the most significant. And then the limit of negative x to the power of 5th as x approaches to positive infinite would be negative infinite. So for the rational functions, which are the most common ones in the limits at infinity, we're going to start by starting with the most popular one. So let's just write down a fraction and say that what happens if I try to make the denominator of this function bigger and bigger? 1 over 1000. Notice that the value is getting smaller and smaller by increasing the denominator number. So as I want to reach a number which is crazy big, like infinite, which is also undefined, it's going to be 1 over something extremely big that's going to make it to almost 0, but it's never going to reach it. And the same goes for the negative numbers. When I want to apply the negatives, the further I go for the negative numbers, the value decreases less by less to a small amount. And the reason is that I'm not never reaching 0, but in limits language, by reaching from x as x approaches to infinite, from the both sides, whether if it's positive or negative infinite, I'm going to get closer and closer to 0, but never reach it. But that's what exactly we need from a limit language. So before we just solve the next three, let's take a look at this. We do have 3 types of fractions by terms of degrees. One is the numerator is bigger than the denominator. The other one is when they're equal. And the other one, which is the last one, is going to be the denominator degree is going to be higher than the numerator. So for this one, as we look and notice, this is a top-heavy function, which means that the numerator is higher by terms from the denominator. So since the higher terms, as we said, are significant, we're going to only write down those. So it's going to be the limit of 4x to the power 5th over 7x squared as x approaches to negative infinite. By simplifying, I'm going to reach the limit of 4/7 x cubed. And if we directly substitute the value for the infinite, we're going to get a huge amount of negative infinite cubed, so it's going to be negative cubed. And for the next one, we notice that this function is going to be a bottom heavy since the degree of the denominator is higher. So writing down the significant ones, it's going to be x squared over x to the power of fourth, which is going to be 1 over x squared as x approaches to infinite. So if you remember, we just solved this, but right now this is with a degree which is squared on the denominator. So still, it's going to make no difference, and 1 out of an infinite number is going to be 0. And for the next one, this is a bit different. As we notice, the degree of the numerator and denominator highest terms are actually equal. So what happens is to write down the limits right here. For the significant parts, and it's going to be 7x cubed over 3x cubed. And that's going to make it the limit, the value is going to be 7/3. So let's take a look at this. And what's the main reason that we're just writing down the highest terms? Because we never explained it. For this one, let's say that we could simplify all of them or divide all of the terms from the numerator and the denominator by the highest term of each side. So let's say that for this one, it's going to be 7x cubed over x3 plus 4x over x cubed, and it's going to be -1 over x cubed. And the same goes for this part. It's going to be 3x cubed over x cubed. Wait, hold on. Minus 5x squared over x cubed plus 8 over x cubed. Notice from the most popular limit at infinity that we just solved, the value of these ones that I'm pointing, it's going to be 0. Since all of these are going to be bottom heavy, so they're going to be insignificant, and the only things that we're going to get is a 7 and a 3, which is going to be 7/3. Before I solve these two, from what we just learned, is that if there is a function, a rational function, that the degree of the numerator and the denominator are equal, we just only need to write down a coefficient. So coefficient is the number that gets behind the variable, which is the x. So I just wrote down if there's a need for this. So here 6 is coefficient, which is a constant number gets behind the variable, and that's going to be x. It could be anything, it could be y, it could be z, and we call the plus or negative an operator. And for the last one, eta is going to be a constant number, or called in the function as a constant. So let's solve these ones. This one it is a bit tricky. So we just need to write down the highest terms. For the top, it's going to be, let me just write this quick. It's going to be x to the power fourth, but for this one, it's going to be, so as we see, it's going to be square root of x to the power of 6 plus 3x cubed. I'm sorry, x squared. And the highest term is going to be x square root of x to the power of 6th. And this one is going to be x cubed. We don't need to write down the absolute value for this one. And the reason is we already are applying at a positive infinite point. So we're going to write down x to the power of fourth over x cubed, which is going to be x, and it's going to be positive infinite. And for this one, it goes the same way. All I need to do is to write down the highest term of the top, which is going to be square root of x squared, over 2x. So this one is going to be x, and we notice that the degrees are the same and equal. So the only thing that we do need to have is to write down the coefficient. And it's going to be the limit of half, or 1/2, or anything you want to call it. It's going to be a constant thing, a constant function, and it's going to be 1/2. Now for the last part, we're going to take a look at exponential and the logarithmic functions. So for a reminder, I just wrote down the e number. It's 2.71, but I just add up a little bit more. It's not that necessarily, but there we go. So for the first one, the limit of x to the power of x, the limit of e to the power of x as x approaches to positive infinite. If I want to directly substitute the positive infinite to the power degree, it's going to be, we do know that e is between 2 and 3, so it's going to be a number, a positive constant number, which is not kind of constant, but anyway, to the power of infinite. So it's going to be a large number, and it's going to be infinite. And for the second part, we do know that if we want to apply a negative number to the degree and the power of e, it's going to be reversed. So this is going to be a limit of, we can rewrite it as a limit of 1 over e to the power of x as x approaches to positive infinite. And for this one, we did see that this one was a big number, and it's an infinite number, so it's going to be 1 over infinite, and the final answer is going to be 0. But the big one and the last part is kind of a bit tricky. Feel free to pause the video. This is actually a good one. If I want to directly substitute, I'm going to get to a infinite over infinite answer, which is going to be undefined, and that's going to be a bit complicated and confusing. So what I could do is that hopefully I reach this answer, which I know it might be weird to say this, but it's a good thing because I could use the L'Hopital rule. So if I want to take a derivative, which you guys will learn, but I'm going to make a video about it. It's going to be basically we're just gonna differentiate about of each side. So it's gonna be 3x squared over x e to the power of x. So when we reach the L'Hopital rule, the e to the power of x is gonna be the same. And still we're gonna get the infinite over infinite. So once again, we're gonna just apply the L'Hopital rule, and it's gonna be 6x over e to the power of x. So still the same till we get to a constant number over e to the x. And it's gonna be 6 over infinite, if we want to directly substitute the infinite. And that will be 0.